Good morning, good evening. My name is Stefan Hoppe. This is a TwinCAT 3 webinar with the topic C++ integration. We will do a quick start and introduction into this topic. First of all, if you like to interact with us, please feel free and insert your questions into this chat area. Don't be shy, so we have a lot of questions and a chance to answer that. First of all, as a quick start, let's talk about TwinCAT 3 at a glance. The engineering of TwinCAT 3 is integrated into Visual Studio. We support that you can implement the code in different languages, everything from ISC 1131, but also C++, which is a topic today, and also MATLAB Simulink. Then we have a concept of modules, which means modules can be implemented in these different languages, but at the end you compile it. Programmer compiles his own module, and then you can share that binary module with your colleague, so he has a chance at the machine to combine the binary modules to let them interact, even they run on multiple different cores. So we expect that a machine builder in a short time has a huge library of binary modules, being able to reduce the engineering time for machines, because he can reuse a lot of modules, 80%, 90%, and just focus on what's the new job to do here and to solve here. So the pre-requirements for specific implementation for C++. We run on every Windows, Microsoft PC, XP, 7, 8, on both platforms, x86, x64 platforms. You need one of the Visual Studio copies for Visual Studio 2010, 12 or 13. The minimum level professional would be fine, but feel free to also make use of premium or ultimate. And again, be aware we are using the Visual Studio environment to hook in, but we are not a reseller of Visual Studio. For C++ development, you need a Windows driver kit, the version 7.1. This is what we have released and tested in our environment. It's available on the web. It's about 700 megabyte. And please see the backup information system, which is our documentation. It's also available in the web, where you see exactly where to download and what parts you need really to install. And well, then of course you need the TwinCAT 3, a full version for which also supports both runtime and engineering. It's about 500 megabyte as a setup. And it provides you a free charge for engineering with C++ and also PLC. So yeah, download that from the web. How does it work? If you install TwinCAT 3 on a PC, the installation routine is checking is Visual Studio available on that machine or not. In case nothing is available from Visual Studio, which is fine for the PLC programmers, then we provide a royalty-free Visual Studio 2010 shell and then hook in all kind of ISC 1131 programming environments. You can definitely also execute C++ and MATLAB modules here, but because there is no compiler, no debugging environment, you can only execute them, but not program and debug them. So for that, as mentioned before, you need one of the Visual Studio versions, Professional, Premium, Ultimate, and then TwinCAT installation setup will hook into that environment, and then you have the full version providing all features from the PLC side, from the right side here, but also being able to debug and implement C++. You can do C# programming, but this is only fine for IT services, connectors, databases, your front end, your user interface, but C# cannot be executed in kernel mode for hard real time. Well, this is also an overview. So we integrate everything into Visual Studio on the left side here. So with the system manager, with all the configuration of IOs and keeping everything together. But then we have the part of C# for non-real-time programming and execution, but also the programming environment for everything on ISC 1131, which is using an ISC compiler. But what we implement in C, C++ is handled by the Microsoft C compiler and then downloaded into the environment. Yes, you could even take a different C++ compiler, but yeah, we think Microsoft has one of the best compilers on the market. What do you need on the runtime side? So first of all, take whatever PC. We appreciate you make use of the back of PCs, which could be an industrial PC on the right side, or on top it could also be a DIN rail PC. For C++, you definitely need a Windows XP or Windows 7.8 or the embedded standard versions of that. So standard 2009 or standard 7. Sorry. But we are not supporting Windows CE for to execute C++. So CE is only available for PLC. And then you need the TwinCAT 3 XR runtime. It's a setup of about 100 megabyte because, well, it's just a runtime. It is not the engineering environment to save space. Definitely at the machine you normally do not need the Windows driver kit and the full Visual Studio, because you do debugging and monitoring remotely from the engineering PC. The license, first of all, you can start without any license, because you can always, and I mean always renew for having a 7-day trial full featured, so without any feature limitations. But we trust our customers. We do not expect they are running into production halls on Sunday evening to renew for a full week. So at the end you will have a commercial license. If you only do C++ runtime, then it's TC 1300, and the XX is for the platform. So on small CPUs with less CPU power, you pay less, and with higher CPU, with multi-core and high-speed CPUs, you pay more. And so that's the XX form. If you need a combined runtime like PLC and C++, it would be TC 1210. Okay, and then we have a wizard which makes your life easier, but I'm stopping here my presentation and just switch over to make a live demonstration here. So I have Visual Studio on my machine. So I start Visual Studio and I select New, go to Project, and here you see that it's a full Visual Studio. I can do C# programming, whatever, but Microsoft, we integrated smoothly here into this environment. Sample controller driver. This is my project about. I say OK, and I quickly have here my environment. So now I right click to C++, add new item, and I get a file, and I say OK, I want to make a sample controller, add, and here I get my wizard. So whatever I start with, I can add features later on, but mostly if we do a quick start, we want that our C++ code is executed cyclically, and we want to also access the field path system later. So we are selecting this option, module class with cyclic IO. This would run cyclically. Later on, if you say, no, well, I just need a C++ routine which is just executing some specific calculation, and it should only be executed on demand, being called from another C++ module or from PLC logic, then even the first option would be fine. Okay, here we start with this one. We say add, and I just keep the module here, call it controller 1 module 1, whatever name. Okay, so we have that file, and this would also be able to be executed and to be able to run. So I go quickly to some areas. One of the area is the routine called cyclic update, which you see here. And this routine is now called cyclically from that part of the task with a specific cycle time which we can configure from the outside world. So what I do is I just change a little bit of the code. I just do counter plus plus, so I'm incrementing a counter on each cycle time, and then the counter is assigned to value, and value somehow magically is assigned to an output area. First time I just want to quickly run this demo, and after that we can change code. So this is fine. I want to compile this, so I right click. Oh, I want to debug later, so I select debug here. Now I right click here and compile everything. This is important. Succeeded, nothing happened, that's great. This is now something like a C++ class, which you could compare in the PLC world to a function block. And now we have to create an instance of that class, so a runtime instance. So I right click here, set new item, then I have a wizard looking into my project that I have a controller 1 module 1. Well, this is the only class I implemented, and I create now one instance, one runtime instance of this class. Okay, did it. Here we go, and here are exactly my input and output variables which have been created by the wizard, and we see later on how to extend that. Okay, in the C++ area, we want to debug later on, so I have to select this here, enable the C++ debugger. And now, of course, this runtime module somehow has to be triggered by a task. So looking to the real-time context here, right now there is no task available. So I go to System, right-click on Task, add a new task. It's called Task 1, which is fine. This task is automatically started and it loops in 10 milliseconds, which is pretty slow. But anyway, now selecting back here my runtime module. Now I select task, and here we go, task 1 is available. So I select task number 1. Okay, this is a good moment to save everything and to download everything to hard real time. Right now I do it here on my x86 based Windows 7 notebook. So I activate the configuration. Do you really want to do that? Yes. Restart in runtime mode? Yes. So as you see here on the green icon, now everything is running. But of course you will not trust me. Huh? Okay. So I go to the my value, which is incrementing. I go to online, and I definitely see here that the value is incrementing. Okay, how can we do debugging? Well, debugging is pretty easy. We go to the source code area, we select right click, and we go to debug, start new instance, and immediately I have an environment with a so-called TwinCAT Live Watch window, which I explain a little bit later. This Live Watch window provides all parameters from my task, from my runtime module. I double click here on mCounter, and here we see that mCounter is looping. The code is still executed. I see the variable. We are not stopping the code. I even can double click into this cell and provide another variable, like another value, like 42, because that's the solution for everything, right? And now you see 42 is here listed in red brackets, and by clicking here on this green icon, which I do now, we just overwrite the value down into the C++ code, which is still executed cyclically. So this is what we definitely optimized in the Microsoft Visual Studio environment. You do not have to set a breakpoint, which you can do. So I'm now going on toggle F9 breakpoint. Now the code is stopping. Now I see the Microsoft Watch window and the call stack, but of course the execution of my counter stopped, which would maybe crash a machine or something like that. You can do a step over. You can, of course, toggle again the breakpoint, and you can continue. I'm using here the menu because my function keys are locked by another system right now. Now it's executed again. We can continue counting. That's great. So I stop it by switching back to config mode. Okay. Well, this was a really quick jump start on the execution and how to make a project and so on. The big question is, how can I extend these values? I want to have different input outputs. Well, therefore, you do not go to header files or source code level. You do it in a graphical way. So you double click on TMC file, which stands for TwinCAT module class description, and then you get a designer, and this designer provides all kind of functionalities which are available in a module. So what we do here is we go to symbols and then click on add, and then we have a new symbol called symbol 4, which we don't like, of course, so we double click on symbol 4 and we change it to my counter. And this my counter is also an unsigned integer. Here we go. Okay. And that's it. And for the input, we want to make a complex data structure. So first of all, we create a new data type. The new data type, it is called my data access. And it's a struct, and we enter the struct. So we press plus, we have one sub item, I press another time plus, we have two sub items. So sub item number 1 I change its x position, it's an integer. Now I want to have it as a real. That's fine, and I want to go to double click to sub item 2, and that's y pos, and that's also real. Great. And now I have a new data type, my access data, and this is what I want to create as an input. So I go here to input, I say plus. Here's my new variable called symbol 4 by default. I change it. I say, well, this is access 1, and it's not an integer. It's from type my data access, which I previously created. Okay, here we go. So now we created everything here locally. But in a second, we will provide that in our code area. By the way, it's same with providing a method call. I go to data types, right click and say add new interface. Here's my interface. I click into that interface. I call it iState machine. I enter some methods for that state machine. So method 1 should be execute, and execute gets a parameter. The parameter is brun. So if brun is true, then the loop should be executed. And so it's a boolean. And another method should be switch runtime. Switch state, of course. So set new state, and we provide an n new state as an unsigned integer. Here we go. Okay, good moment to save everything. We defined as a template this iState machine. Now we have to add that to our module. Same as we created my data access and we put that to the input area. Now we have to edit this new interface here to our module. I select implemented interfaces. I click on plus. I get a list on all available interfaces which I can add to my project. At the top line I see iState machine. I select OK. And now it's available in my environment. So clicking, right click here on my C++ project, now I execute the TwinCAT TMC code generator. And this code generator is taking all the information which I created here, which I entered here in my TMC editor, and creates exactly the header files in the background. So now we can check the code behind. We can go to services, for example, and we see that, for example, here automatically the designer created my data access as a template, as a structure, and I see my input variables with my variable access1 from data type my data access, and I also see my counter, which is in the output area. So again, this TMC file is an XML file, and with this designer you are working at the end on the XML file, and by calling this TwinCAT code TMC code generator, out of this XML file we generate the source and header files. Going to the source code, just to the bottom, we also see that my new interfaces are implemented. So I have a new method called execute with a bool, and we also see set new state. So this time it's pretty easy now, for example, to have this variable be run and go to our cyclic execution area. Here we go, and just put this in brackets and ask, okay, if B run is true, then do the execution, otherwise not. So you have something which is cyclically called from the outside world. Yes, that's true, but internally your code is only executed in case the execute is set to true before. So compile it again, rebuild, and you see automatically by opening the input outputs that we have our access. We double click here, and we would be able to map it now to whatever input outputs which are available. I have my counter, and this is also available to the outside world. So let's switch back to the presentation and continue here. So I already mentioned the wizard. I already mentioned that we have a graphical designer to do the configuration, which is in an XML file, and then we make use of the code generator. Again, the reason why we do it behind is that we think about automatic code generation in the future. Maybe you have a description of your machine in an Excel sheet or in your database, so you can write your own converter to get the data out of the Excel sheet, put it into the XML file, and then do an automatic compilation and download down to the machine. And yes, we have tools for that. It's called the TwinCAT Automation interface. So I made a demo of this editor. This is a cyclic routine, cyclic update, where you put your code into. As a target platform, we have RT for both x86, so which is 32-bit, but also x64 operating system. We have something which is called user mode, but it's not enough to only select user mode here. You also have to start Visual Studio in a different way. And so in this case, you have to contact your local backoff person. This is just for very, very specific companies doing writing a driver, accessing, for example, the DP-RAM to make their own driver to their own hardware card. And in this case, you deal with pointers, and you want to run that first of all more in the user mode instead of it later on in the hard real time. User mode is not providing hard real time, so it's just a development help. CE you can select, again, as mentioned before, this is available for PLC only, not for C++ runtime today. And one note, the PLC environment, the PLC modules are, well, definitely compiled to native code, but the PLC provides a so-called hosted runtime environment, which means while the machine is running, without stopping the machine, you can change the PLC logic and download that in a so-called online change way. So the hosted environment is receiving the new PLC logic, and when everything is downloaded, there's a hot swap between two cycles. And this is different to C++. So this is also a native kernel driver, but it's not a hosted environment. And so in case you want to stop something and make changes in your C++ logic, you definitely have to stop the execution of C++ module first. If you have a combined environment, PLC and C++, and you make a hot change of the PLC part only, that's fine, because the C++ still keeps running in the memory, there's no change, and that's fine. As mentioned, we changed the behavior of the standard debugger, so if you do normal implementation of C# or C++ or Java code, and you execute your code, you do not see any watch window. You have to make use of printf, something like that. And then first set a breakpoint, and then you get really the snapshot and the call stack. And this is different because we provide a so-called TwinCAT live watch window, which I showed you live. And this allows that without breakpoints you can monitor the execution of your code and even overwrite values. Well, let's talk about the module concept in general. So we have a module language, and therefore we need a module description. So all the red parts, the module description, the state machine, and the interface to provide all kind of information what is available, this has to be done in every module, and the blue parts are optional, and they describe, well, what optionally could have been available at that module. For example, in my demo I created a new variable in the data area, input and output area. I created a new interface on my state machine, and I executed my module in context of task number 1. The state machine behind is something to switch the module from the init, from the config mode into the deterministic execution, into the operational mode. And you see all these transitions, set object state PS or SO, from safe operation to operational, in the code, in the module 1 C++ code, so you can interact there. And so why do we need this state machine? Well, because again, we have to load the memory, the module into memory. If modules want to interact at runtime with each other, one module wants to talk, wants to map data and interact with another module or by a pointer, then these modules first of all have to find each other, exchange pointer information and so on. You find detailed information in our information system, so just go to infosys.beckhoff.com and then navigate to TwinCAT 3, to the TC3 engineering, and then the C++ area, where you have two parts. One is a C++ reference, and then you have a C++ samples area. Okay, I already mentioned the context, so here same, we executed our module in task 1, and task 1 was also executed on core 1. And then if you want to do sorry, that was too quick. So in case you want to do startup parameters, so that's also easy to provide. So there's a mechanism called parameter as its own category, and you also define it in the TMC editor, pretty easy. But then this is not available to be mapped to physical input outputs. Instead, it's an internal parameter, which you see here in your system manager in the Visual Studio. So you can, in the Visual Studio, provide some startup parameters and set it to specific values. That's pretty helpful. In earlier days, you would have implemented something like an INI file mechanism or XML file mechanism to read parameters on startup. And here it's much more easier. One of the interesting questions is, hey, if TwinCAT 3 is executing up to 250 cores, this is what our system is designed for. And if I can create as many tasks which are just limited by memory here, so then the task is executed on specific cores, and the tasks are triggering modules, and the modules are somewhere in the kernel memory, and then the modules being executed from different tasks should somehow interact with each other, even they are running in different cycle times. Hey, so how can I guarantee data consistency, or how can I protect for re-entrance issues? And these are the next 4 slides a little bit about. First of all, there are 4 different opportunities for implementation. First is pretty stupid. It's mapping of data areas. Then it's mapping of data pointers. So that's just configuration, pretty easy done. Then you can call interfaces, of course, method calls. And then at the end, you can also do ADS messages, sending ADS messages between different modules. Number 1, 2, and 3 is being able to execute it in hard real time. Opportunity number 4, ADS messages, is not for hard real time. So what is mapping of data areas? Well, instead of mapping an output to a physical output on field path, you can of course do a horizontal mapping. So from an output from the PLC code could be mapped as an input to a C++ code, or here the other way around. This could be a mapping for single data variables, but also for complex data types. Because TwinCAT is taking a copy and moving that copy as an input to the other side or an output, it's absolutely data consistent. It could be done between all data areas from and to PLC and MATLAB and so on. TwinCAT guarantees data consistency. It's easy, it's extreme easy, and it's done in the PLC in the task cycle time, which you can scale down to 100 microsecond or even a 50 microsecond. So this is extremely easy to change data between different modules, and because you implemented different functionalities in different modules in an object-oriented way. If that speed is not enough, then make use of pointers. Pointers are really available whenever your C++ code is executed, and you have exactly the access because it's a pointer to whatever input-output area at that moment that line of code is executed in the C++ area. But be aware, and everybody you are aware of that, with pointers you have to take care on data consistency on your own. So if you write from a different core in 100 microsecond to whatever other parts with a pointer, be aware of data consistency. Data consistency could also be provided by calling methods. So if you just have one caller, for example, the PLC can execute a function block and then calling a C++ interface, which is implemented here. And if it's just a one-to-one relationship, then it's fine. You don't have to protect something. But if you have multiple callers which want to, maybe even at the same time call into your method, then you have to make use of semaphores and protect your data and your execution here. And as mentioned before, send ADS messages. ADS is the backup way how to exchange data between all kind of TwinCAT products and supplement products and so on. And ADS is a protocol which could be vertical but also horizontal between kernel mode and user mode for HMI, for your own driver. It's royalty free. We have a lot of sample code. It can be executed even over network, but of course then you lose hard real time, but definitely it's guaranteeing data consistency because everything is serialized over that ADS protocol. Well, what's coming up? What are we currently working on? Right now we are preparing an update of the Beckhoff SDK to also provide floating point format support like sprintf and scanf. And then we are preparing a new function, which is a real on its own product with royal fees. The temporary name today is TwinCAT 3 TCP UDP RT, which means out of the C++, you can, out of the kernel mode, you can open a TCP or UDP port and then communicate to your TCP or UDP partners in the network. Be aware, it's not a fully blown up TCP stack, so it's a very small, limited subset of that. But anyway, of course, it's much more faster than instead of first giving data with ADS calls to the user mode and then there make use of WinSockets to call it to the outside world. And then, which is also pretty cool, I think, if you define a method in a C++ module, you can just activate a checkbox for that method call, and then this method call is automatically available in the OPC UA server on the same controller to the outside IT world, which means this is an international IAC standard, OPC UA, and this allows that whichever OPC UA client in the world on whichever operating system can browse to the OPC UA namespace, find the method, figure out the input-output parameters of that method, and then even execute that method. And the UA server is internally then executing the method call in the C++ environment. So it's a combination from the IT world, from the non-real-time IT world down into hard real-time deterministic execution. Well, these have been the seminar. We have run a little bit out of time, but hopefully that information was valuable. In case you want to see other webinars, please go to this area, www.beckhoff.com/webinar. In case you want send us some feedback or proposal, please feel free, don't be shy. Send feedback to gotowebinar@beckhoff.com. And yeah, that was my seminar. Thanks a lot and thanks for listening. Bye.